I have a manometer here. Nothing too crazy. I've got an open end tube here, and you can see there's a measuring stick, and I have some fluid filled with water, but originally this was be mercury because Torricelli's earliest barometer used mercury. In any case, what I'm going to do is I'm going to take a syringe and I'm going to attach it to the enclosed tube, and now I'm going to make the space smaller for the same amount of gas that's trapped in this area. So by me making the space of the volume smaller, okay, the pressure is going to increase. So I am going to, Boyle's law, lower the volume by forcing the gas molecules into a smaller space is going to increase the pressure. The manometer is going to measure that increase in pressure. When the pressure was equal, these levels were equal, because the pressure in the inside of this tube is equal to the pressure pushing down in this open container. So the force on this liquid level is the same as the force on this liquid's level, and thus you have equal pressure. Now by increasing the pressure, and I'm doing this by making the volume smaller, stuffing the same amount of gases in the same temperature and pressure, and making a smaller volume, I'm increasing the pressure. And what we can do is we can measure the difference, okay, of these liquids to measure the pressure. Right now, if I wanted to measure the pressure, if this was mercury, we would say that I'm supporting, if this is 4, and let's pretend this is approximately 23, okay, so this is 19. So from this point here, I'm measuring 19, okay, millimeters. Okay, now of course this I just measured 19 centimeters. So that's 190 millimeters of fluid I'm supporting upward. And I would say that the pressure in this area is higher than the atmospheric pressure pushing down. Right? Manometers use a differential of pressure to measure. So right now, the pressure in this syringe, which is connected, is 190 millimeters of mercury higher than atmospheric pressure, right? There's two forces. There's a force pushing down here and the force pushing down here. Who's winning? Clearly this side is winning by 190 millimeters of mercury, which is, by the way, is a torr. So we would say the pressure in here, if the atmospheric pressure was 760 torr, it'd be 760 plus 190, and that's how we measure the pressure here. Okay, if we go the opposite way, make them equal out again, and now I'm going to lower the pressure by making the volume larger. Whoa, how much higher in pressure is the atmospheric pressure? Well, this pressure is lowered, and this pressure on the open end is winning. Let's pretend it's also 19 centimeters, so let's make that 190 millimeters of mercury. So now the pressure in here is less than atmospheric pressure by 190, and so we would do 760 minus, okay, 190, and that would be the pressure here. So this pressure here is lower. Clearly you can see the atmospheric pressure is winning by 190 millimeters of mercury, okay? And again, the pressure in here is 760 minus. When we did the other side, we did what? We increased the pressure. We did what? We said, well, this is pushing back on the atmosphere plus it's supporting the column. So this is equal to the pressure outside, but you have to add 190 to it in this case if we're going to use that. Okay, so manometers are used, either subtracting. Here we're equal. Here this side is less than the atmospheric pressure pushing down by this much. And here, the gas here is less than the atmospheric pressure by that much. Now, if we don't have mercury, we can change that into water. So, I'm sorry, if this is water and not mercury, we can compare it to mercury's density by height times density equals height times density. Because if you have mercury, okay, mercury is 13.6 times more dense than water. So therefore, its height is going to be 13 times smaller. A heavier volume of water, okay, cylinder being supported. Remember, we're supporting a certain weight, okay? And that weight, for the same amount of weight of mercury, it's going to be a lot less volume. So if this was water and I'm going to convert it to mercury, okay, I take my, if we're going to use 190 millimeters, I divide it by 13.6, and that would be the height in mercury. So if we don't have water, we can certainly get there by doing those differences. So that's a little basics of manometers.
Just a short video to show you some of the properties of a piezoelectric ceramic material. In this case, I have a sample, a small disc of piezoelectric ceramic. It's the dirty silver colored disc, and it's bonded to a brass disc. You can buy these for a very low price in many outlets. They're called piezo buzzer discs in some cases. At any rate, it's a piece of piezoelectric ceramic, very thin disc shape, bonded on one side to a piece of brass. And I'm going to connect it to a voltmeter by setting the disc on one thin brass sheet that's connected to the negative lead of the voltmeter, and I'm going to connect the upper surface of the disc through this brass rod into the positive lead of the voltmeter. What I'm going to do now is press downward on this brass disc and watch the voltmeter reading. See, it goes positive and then it swings negative as I release the pressure. So I'm going to apply pressure and then release pressure. When I apply pressure, you'll see the voltage swing positive. When I release, you'll see it swing back negative. Okay, so I'm going to apply and release. Apply and release. Apply and release. And you can see I'm getting about 2 or 3 volts with this small amount of pressure. Another aspect of the disc I'd like to illustrate is the fact that piezoelectric ceramics, and in fact all ferroelectric materials, are pyroelectric, which means that they respond to heat. If I raise the temperature, I also generate a voltage. And I'm going to do that with this hairdryer. Just to convince you that it's not the sound of the hairdryer that's doing it, I'm going to turn on the hairdryer, point it away from the disc, and then I'm going to rotate it toward the disc and watch the voltmeter as I rotate toward the disc and away from the disc. Rotating toward the disc, rotating away from the disc, toward the disc, away from the disc. So here we have a voltage produced by heating of the material, and notice that the polarity was negative. The voltage produced was negative. This is a very nice test of a ceramic material. If you don't know which direction the polarization vector is, connect a voltmeter to it, heat up the material, and if you create a positive voltage, that means that the polarization vector is in the direction that you've connected the electrodes from negative to positive. If it's negative, as in this case, it means that the polarization vector is in the opposite direction, in this case from the positive down to the negative electrode. So those are just 2 of the features of piezoelectric ceramics. We see the voltage produced by an applied pressure, and we see the voltage produced by a temperature change. Thank you.
Welcome to Lunchbox Sessions, bite-sized industrial training.
Hello, this is Carl at lunchboxsessions.com. In this video, we're going to look at basic functions of a very important pressure valve called a relief valve. Many hydraulic systems use a pressure relief valve as the primary means to limit maximum system pressure. Without a relief valve in place, pressures could potentially build to an excessive level where the machine might be damaged, or perhaps a hose might burst, endangering human lives. The type of relief valve we will be examining is the simplest style with only one poppet and one spring. It is known as the direct acting relief valve. This live schematic shows a fixed displacement pump sending a flow of 10 gallons per minute through the system. Our directional control valve will remain energized in the cylinder extend position. The relief valve is shown in cutaway form so that we can see all of the details and actions of the relief valve as it responds. The system pressure is indicating 200 psi, which is calculated by looking at the mass being lifted, 2,000 pounds, divided by the 10 square inch surface area on the bottom of the piston. The controls show that the relief valve is set to 300 psi. But how do we know this? The only true way to know the relief setting pressure is to observe the system in action and the values on the system pressure gauge. Let's add a 2,000 pound brick for 4,000 pounds total divided by 10 square inches, and we did not achieve 400 psi. The cylinder crashed back down to the bottom, and the maximum pressure on the system gauge indicates 300 psi. When flow from the pump can take no other path than through the relief valve, the pressure value on the system gauge then indicates the true setting of the relief valve. Let's add 3 more bricks for a total of 10,010 pounds. We would need to trap a system pressure of 1,001 psi to lift this load. Now, if we tension the spring on the relief valve, we notice that the system pressure is climbing as the relief valve poppet pushes against the flow. As the relief valve can only be adjusted up to 1,000 psi, we are unable to lift the load on the cylinder. We simply cannot trap the required pressure in the system. Watch what happens as we remove 1 brick for an 8,000 pound remaining load divided by 10 square inches for 800 psi system pressure. The cylinder starts to lift, but notice that the relief valve is not closed. Let's once again add a brick and remove a brick while watching the poppet in the relief valve. Removing a brick allowed the poppet to advance upward, but the relief valve does not quite close. Removing 1 more brick for 600 psi system pressure, we see that the relief valve has closed completely and that the cylinder has increased speed. Again, let's add the 4th brick and remove it while watching the relief valve and the cylinder. Remember that the relief valve is set to 1,000 psi, but clearly the valve opens at 800 psi and begins to direct at least some of the system flow back to tank. In this case, the cracking pressure is 800 psi, where the relief valve setting is actually 1,000 psi. The difference between the cracking pressure and the setting pressure for this particular relief valve is 200 psi. In order to lift the system at maximum possible speed with an 800 pound load, the relief valve would have to be set a little higher than 1,000 psi. In future videos, we will examine pressure override in more detail and look at more complex relief valve designs.
We have hundreds of interactive resources like this live schematic, so you can try out your wild ideas without blowing anything up. Get started at lunchboxsessions.com.